Okay, if you've looked at the webpage, you will discover that I've put up some additional little videos. I've put up one on z-scores and the normal distribution. I think I've put up 3 or 4 little instructional videos. They're not mine. They're by somebody who is really good at animation and explaining this sort of stuff in a very nice, tight, concise kind of way. So after I've talked today, I would recommend that you go back and look at those videos and use those as sort of a guide. What we want to do today is get to the point where we can talk about what we want to do our first statistical test, and that means I want to talk about the most basic, crudest kind of possible statistical test, and that's going to be a 95% confidence interval. Okay. So I have a lot of notes here. I'm going to skip over that because I think you can get all of that information out of these little videos, and that will speed things up and save us some time. Okay. So the idea is this. I sort of alluded to that earlier, and that is, we know that there's some underlying distribution to our numbers. So if we were to go out and take body weights of organisms, we could measure students, and we would get a whole series of body weights. And we could then compute what the average is. And we talked about that last time. That average is a measure of central tendency. Well, it's a parameter, right? Or it's a statistic. The average is a statistic which we're using to describe this population. Okay? But I understand if I had taken a slightly different sample, right, that included 5 other people or 3 other people, I would have gotten a different average. So I know that there's a certain amount of variability associated with that average. Okay? All right. If, on the other hand, I have the complete sample and I compute the average, then I come up with something which is called mu, which is the true mean of the population. Mu is a parameter of the distribution. X bar is my average. It's my estimate of the parameter. It is a statistic that I use to estimate the parameter. Okay? So X bar is an estimate. Mu is the true value. Okay? I'd like to know what the true value is. But all I've got is a sample. So the question is, can I figure out, can I get closer to what that true value is? And the answer is yes, I can. So we already know that X bar is equal to the sum from from I equals 1 to n of x sub I divided by n. That's our equation for the average. Your phone does that for you, your calculator does it for you, Excel does it for you, whatever. Mu, on the other hand, is equal to the integral of xi times f at xi dx from minus infinity to positive infinity. How many of you have had calculus? Anybody? One person? The rest of you have not had calculus, so you have no idea what the integral means. That's just the continuous case of that. These two things are functionally exactly the same, except that this one goes from minus infinity to plus infinity, and this one goes from I equals 1 to n, where n is your sample size. If you don't know calculus, fine. Later on in the semester, I will give you everything you need to know about calculus in about 5 minutes. Okay? This has a name. We call this the first central moment. All right, fine, great. I obviously can't compute this because I have to go from minus infinity to plus infinity, right? And that f thing right there is sort of confusing. If you've not had calculus, you probably don't know what a function is. Are you guys familiar with the term trickle-down economics? Do you know where that term comes from? We just did a huge episode of Trickle-Down Economics a couple of years ago. It was the tax cut. You guys remember the tax cut that Trump gave us? You don't remember because it didn't mean anything to you. Why? Because the tax cut for you is maybe a pack of cigarettes over your year's earnings. The tax cut, on the other hand, for Jeff Bezos and Tim Cook and Bill Gates was in the millions and millions and millions of dollars. The tax cut for Trump was huge. It was a tax cut for the rich. And the idea was that if you cut taxes for big business, that they're going to take all that extra money and invest it in that business and grow jobs. And then you will benefit. That's called trickle-down economics. That's based on something called the Laffer curve, L-A-F-F-E-R curve. And it turns out that the Laffer curve is not a function. A function is something that has only one value for each value of x, like this bell-shaped curve. On the other hand, that is not a function because it has two values of y for one value of x. That's not a function, that is. So trickle-down economics is not a function. It doesn't work. Has it ever worked? No, it hasn't. Every time the government cuts taxes in an effort to grow the economy, they don't. But we still do it. Still. That's the bell-shaped curve. Let's look at that curve. Okay? That curve is referred to as a probability distribution. Okay? The area underneath that curve is equal to 1. The area underneath that curve is equal to 1. If I integrate this from minus infinity to plus infinity, so forget about the xi, if I just take the integral of xi from minus infinity to plus infinity, that area is going to equal 1. That's what makes it a probability. Probability is the mathematics of the numbers between 0 and 1. It's the easiest of all possible mathematics. All the other mathematics, you have imaginary numbers and numbers that go from minus infinity to plus. It's all complicated. You have to worry about all the numbers. Not in probability. You only care about numbers between 0 and 1. What could be easier? Think about this. Think about the execution of Christ. Christ is nailed up on the cross. At the foot of the cross are these Roman soldiers. What do? They're drawing lots, right? To see who gets Christ's clothes. Why? Are they gambling? No. Why are they drawing lots? They're trying to find out who God wants to have the clothes. Because they don't understand the notion of probability. Why don't they understand the notion of probability? What number system were they using? They thought that whoever got the shortest straw was chosen by God. They didn't realize it was a stochastic process. How could they possibly know it was a stochastic process if they didn't know about probability? Why didn't they know about probability? Because what number system were they using? Roman numerals. What's the Roman numeral for 50? Or for 100? C. For 50? L. For 10? X. For 5? V. For 1? I. What's the Roman numeral for 0?
There isn't one.
There is none. In other words, the Romans had no concept of nothingness. If you can't understand 0, there's no way you can understand probabilities. That's the problem they faced. We don't have that problem. All right. Let's write an equation for that curve right there. It's easy. G at x equals, it's lousy, it's P of whatever. P of x is equal to 1 over the square root of 2 pi times e raised to the minus x squared divided by 2, and that's from minus infinity is less than x is less than positive infinity. There's the equation for that curve. That's referred to as a PDF. Hey, Adobe, now you know where Adobe got the idea. A PDF file. No, PDF stands for probability density function. If I take the integral of that, it's going to equal 1. All right. Hey, let's do this. When I do this, I say x is distributed as n 0, 1. So my variable x is normally distributed. It's distributed, the tilde means distributed as a normal distribution, and it has two parameters. The first parameter is mu. And in this case, mu is equal to 0. The second parameter is the standard deviation. That's the variance. That's sigma. The variance, the square root of the variance, that's how wide the curve is. Okay? So my normal curve could look like that, or it could look like this, and both of those things be normal. The only difference is, what is that parameter? The standard normal curve has mean 0 and variance equal to 1. All right. Let's do this. Let's say that y is equal to mu plus sigma x. I'm defining a new variable. My new variable is y, and y is related to x, right? It's mu plus sigma times x. And when I do that, I get this equation. So that was the equation of a line, right? Everyone see? You remember what the equation of a line was? What's the equation of a line? Y equals m plus bx or something. Okay? A plus bx, whatever. It's a line. Now I'm going to use f of x is equal to 1 over the square root of, oops, need more room, 1 over the square root of sigma times the square root of 2 pi, 1 over sigma times the square root of 2 pi, times e raised to the minus y minus mu quantity squared divided by 2 sigma squared. You see a similarity between those two equations? Oh, holy smokes, you do. What happens if sigma is equal to 1? Well, that becomes 1. And that becomes 1. What if mu is equal to 0? If mu is equal to 0 and sigma is equal to 1, then this equation is exactly like that equation. The point is, I can take any distribution and show the relationship between that distribution and the standard normal. So I can take any normal distribution and make the connection to the standard normal. If you go on the web page, you will find a document titled Inferences About Population Parameters. Download it, because that has essentially everything that I'm giving you right now. Everything. And as you go through that document, and it even has our data set for the flying squirrels. I'll be dipped. Okay? It gives you everything. Holy smoke. And on the very last page is a table for the normal distribution, for the standard normal distribution. And what this table does is it gives you the area underneath this curve from minus infinity up to a particular point. In order to do that, what we do is this. We take our distribution right here, and we're going to convert it a little bit. We're going to change it from a PDF to a CDF, which stands for cumulative density function. And what I'm going to do is I'm going to define it like this. Capital Phi of x is equal to the probability that x is less than or equal to little x. And that's going to be equal to the integral of p at t dt from minus infinity up to x. What that is doing is this. I'm changing my bell-shaped curve from that into this. Okay? But I don't want to think about it like that. I want to think about it like this. My brain is small. And all it's doing is it's giving me the area underneath the curve from minus infinity up to that point right there. Call that A. It's giving me that area. Okay? Hey. What's the total area under the curve? 1. So that's going to be something less than 1. I think I know how we can use this. Okay? Let's do an example. In the video that's on the webpage, where it talks about the normal distribution and the 68, 95, 99% rule, there's a perfect example. Let's do this, though. Let me make a few observations first. Phi at minus x is equal to 1 minus phi at x. The probability that y is less than or equal to y is equal to the probability that mu plus sigma x is less than y. Oh, hey, see what I just did? Here I'm talking about a distribution of y, and I'm converting it to the standard normal. So in other words, no matter what distribution I'm working with, I can work with a standard normal table. Are you going to ever have to do it really? No, because the computer's going to do it for you automatically. R will do it for you automatically. Then, the probability that x is less than or equal to y minus mu over sigma is going to be equal to phi at y minus mu over sigma. Why am I doing this? Why do you have to know this? Because I'm trying to build the case for why it is that you standardize your data. There are times when you're going to standardize your data, and this is why. Okay? So now we want the probability that A is less than or equal to Y is less than or equal to B is going to be equal to phi at B minus mu over sigma minus phi at A minus mu over sigma. Let's do an example. We're going to say y is equal to, whoops. Let's say y is normally distributed with mean 1 and variance equal to 4. Okay? We're going to let A equal 0 and B equal 3. We know that x is normally distributed with mean equal 0 and variance equal 1. Okay? So then, what we're really asking is the probability that 0 is less than or equal to y is less than or equal to 3. In other words, I'm asking the question, what's the probability if we have a variable that's distributed with a mean 1 and a variance of 4, what's the probability that we can choose a value that is going to be between 0 and 3? Okay? You're struggling? It's fine. Don't worry about it. Okay? You're never going to get tested on it. Just looking at it, at some point in the future, you're going to see it again. And you're going to go, I remember that. Oh yeah, I hate that yet. Okay? But whatever it is, it's going to come back, and that little seed is going to be there. That's all we're looking for. Okay? I don't care about the specifics, I care about the gestalt. That's equal to, let's use that idea up there. That's equal to phi at 3 minus 1 divided by 2 minus phi at 0 minus 1 divided by 2. That's equal to phi. 3 minus 1 is 2. 2 divided by 2 is 1. Minus, and I said that phi at minus x is equal to 1 minus phi at x. So I'm going to use that idea because 0 minus 1 is minus, so this is at minus 0.5, right? So that's the same as minus 1 minus phi at a half. If you look, where's that sheet? Where did I put that sheet? Did I hold that thing up? Oh, there it is. Hey, look at that standard normal table. When I was at New Mexico, in a PhD, back in those days when you took a PhD, you had to have 2 languages in order to get the PhD. And I was English is not my first language. My first language is German. So I didn't have any problems getting the first language component out of the way. I just needed a second language. And they wouldn't accept English as my second language. So what I did was I used mathematics as my second language. In particular, I used probability and statistics. And this is a thing of beauty. The very first probability class that I'm in, we're talking about probability distributions and this sort of stuff. And I'm going, oh, but I need the probability table, the distribution table for this weird-ass distribution over here. And the professor just looks at me and laughs and said, son, over here in this building, he knew I was a biologist, he says, over in this building, this is the only distribution you get. Because every other distribution can be derived from this one. The normal distribution is in the family of distributions known as gamma distributions. All the other probability distributions that you typically work with can be derived from that. So they would say, this is the only one you need, son. And he was right. It gets hard, but he was right. Here's what we're doing. Let's think about this. We want I have this curve, and what this table right here is giving me is the area underneath. It's showing me the PDF, but it's really a table for the CDF. That's fine. Just pretend. The answer is going to be the same. But it's giving me the area underneath this curve right here from minus infinity up to that point right there. There's my A. Okay? So phi at 1. I'm going to look up phi at 1. Phi at 1. It's 0.8413. So phi at 1 is equal to 0.8413. So 1, way the hell over here. The area underneath that curve is 0.8413. Okay? Now what I'm doing is I'm going to subtract from that phi at a half. Okay? So what is phi at 0.5? Phi at 0.5 is 0.6915. So I've got minus 1 minus 0.6915. So what does that give me? That gives me, what I'm doing is I'm subtracting off this part right there. So I've got that, and I'm subtracting off that part, which now leaves me with that part. That equals 0.5328. So the area underneath that curve between 0 and 3 is 0.5328. You're sitting there going, whip the F and do. Who the hell cares? How is that going to make me a better biologist? What the hell was I thinking when I signed up for this damn class? Here's why it's so amazing. We can go through lots of other examples, but here's what I want to show you. And this is the point of that little video on the normal distribution and the percent rule. Now perhaps you realize that we can take this curve like this. There's mu. If I go out here and I'm going to, based on the standardization routine, right? I'm going to go out here to 1 sigma and down here to minus 1 sigma. What's the area in there? The area inside there is about 68%. In other words, if I have a class of 500 students, I taught, when I was at New Mexico, I taught anatomy and physiology course. In a lecture hall, there were 1,600 students in a lecture hall. Television cameras, everything was broadcast on screens as I'm up there on the stage lecturing. And it was cool because when you got the exams, 1,600 students, that's a lot of data points. You compute the average, you standardize it, and compute the average. And sure as shit, 2/3 of the students were within 1 standard deviation of the mean. If I go out to 2 standard deviations of the mean, 2 sigma, and minus 2 sigma, I get just about, well, this is another 13.59%, and another 13.59% over there. What is that? That's another 26, so 68 plus 26. Uh, 94 plus the little decimal point, that's about 95%. So between there and there is 95%. And that's exactly what you discovered when you, for 1,600 students, when you looked at the average scores, 95% of the students were between, actually, it's a little bit different. It's 1.96 sigma, 1.96 sigma. if I go out 3 sigma, minus 3 sigma, it's about 97, 98%. Something just really profound happened. Okay, if your brain was working in exactly the right way. In general, in all the classes that you've had, when you've done tested hypotheses and stuff, what's the alpha value that you use?
0.05.
0.05. Well, if that's 95% between there and there, and the area under the curve is 1%, or is 1, that means then 2.5% there, and 2.5 plus 2.5 is 5. See the significance? In other words, when you say, I want my alpha to be 0.05, what you're really saying is, I want to be right 95% of the time, recognizing I'm going to be wrong 5% of the time. So you're saying, my mu, when I estimate my mu, my true value is going to be somewhere between minus 2 sigma and plus 2 sigma. We refer to those things right there as limits, and those are our 95% confidence limits. Okay? In the words of James Dale Smith, holy fucking shit, buckwheat, what just happened? You get it? In other words, we now have a way of defining what the limits are, our confidence limits are for that thing right there. All right. Maybe you don't like 95% confidence limits. Maybe you want 99% confidence limits. What's that going to do? You say, I want 99% confidence limits, then you're going to go all the way out here to 3 sigma and minus 3 sigma. Sociologists like to use 80% confidence intervals. So they're in here like this. Some stats programs that I've seen, and you see this sometimes when you look at graphs. I actually edited a paper once where the authors had the 50% confidence intervals. I'm looking at that going, what the hell is that? I mean, the graphs are great. The graphs may look like you really have some differences there. But man, that's worthless. Hell, that means you're right half the time, wrong half the time. What the hell good is that? Okay. Hey! Here's the rub, though. All of this is based on the normal distribution. The normal distribution assumes you have an infinitely large population. There was this guy way back when, back in the 1930s or so, wrote a paper. He was a statistician, and all of his buddies were biologists. And biologists didn't do a lot of statistical analyses back then. It was a lot of descriptive work. But there was one biologist that was trying to do some statistics, and they were getting it all messed up. So this statistician says, well, this is sort of stupid. I guess I'm going to have to write a paper and explain this nonsense to these biologists. So he did. But because these biologists were his good buddies, he didn't want to offend his buddies. So he wrote the paper and he used a pseudonym. And the pseudonym that he used was student. So the author's name for this paper is Student, which is sort of a slap in the face of all of his biologist friends, because the distribution that he's describing is called student's t-distribution. The implication being that even an effing student can figure this out, and here you are, all these professional biologists, you can't get this shit straight. So he insulted his biologist friends without taking responsibility for insulting his biologist friends. That's where student's t-distribution comes from. Student's t-distribution recognizes the fact that you don't have an infinitely large population. You have a smaller population. Okay? So, you can't use, it's really 1.96. You can't use 1.96 as your limits. You have to use something different. And what student's t-distribution does is it uses different limits depending on how big the sample size is. The interesting thing is this. The interesting thing is this. If your sample size is only 10 observations, your 95% confidence limits are going to be way the hell out here. If you have 30 observations, your confidence limits are going to be about there. If you have 60, your confidence limits are going to be 1.96, 1.96. In other words, the t-distribution converges on the normal distribution as the sample size increases. Students often ask me, how many observations do I need? My initial response is, all of them. Okay? But I know you can't get all of them. Here's what you want. Ideally, you want at least 60 or 120 observations for each parameter that you, unless you know that the data are really nicely bell-shaped. In which case, get 30. At 30, you're going to be basically right there where the normal is. In a worst case scenario, get 10 if you know the data are normally distributed. What happens if your data are not normally distributed? Now we drop down to plan B and figure out something else. Okay? Here's one extra little trick. Okay? There are 2 tricks for dealing with this sort of scenario. 3 tricks. We can use this idea of a confidence interval to construct what the true limit should be. And that's what you're going to do with R this week. You're going to take your flying squirrel data, and you're going to follow the script that I give you in that little video, and you're going to compute, you're going to test the hypothesis that the weights for males is equal to the weights for females. And what you're going to do is you're going to compare the difference in their weights and construct the 95% confidence interval for the difference in their weights. And if the confidence intervals includes the value 0, then you know there's no difference. That's your first statistical test. If the confidence interval for the difference between their weights excludes 0, you know they're different. That's the same thing as doing a t-test for the difference between the means. So when you do that in R, you're going to ask for a t-test. It gives you the t-statistic, and we'll talk about that next time. It also gives you the confidence intervals for the difference between the means. That's your first statistical test. Next time, we'll talk in more detail about how to do a t-test and what it's telling you and what it means, and we'll explain it in this context. Okay? So that's the first point that I wanted to make. The other 2 points are these. There's a thing called a jackknife. Jackknife. I think jackknife, I'll have to check that. I think there's another K in there, I'm not sure. Versus a bootstrap. Sometimes you get stuck and there's no way you can get more observations. It costs too much. Biology is sometimes really expensive. What do you do if you want to know, you want the best possible estimate of mu, but you only have 10 observations? What you can do is use a jackknife. And here's what you do. Jackknife is very easy. You take your 10 observations, remove one, compute the average, write it down. Put that number back in. Remove a second observation, recompute the mean. Compute the third observation. Take out the third observation, compute the mean. So you're going to compute the mean 10 times, each time based on 9 observations. And now you have your estimate of the mean, and now you can compute what the standard deviation of the mean is, which is the standard error of the mean. And now you can compute the 95% confidence interval for the mean. And it'll be goddamn close to what the true value is. That's called a jackknife. A bootstrap is a little bit different. Computationally, more time consuming. So in a jackknife, you leave one out and compute and estimate. And you repeat that until you've left out each observation. In a bootstrap, what you do is you subsample the data set. You're going to take these 3 observations, compute the mean, put them back in. At random, choose another 3 observations, compute the mean, put them back in. At random, take another 3 observations, compute the mean. Do that 1,000 times, and then do the same thing. Both approaches will give you roughly the same answer. Okay? All right. That's where we're stopping today. Go on the web page. Email me if you don't have access to the web page. Make sure you watch those videos. Download these notes right here with the handy-dandy table. Read these. Don't worry about the calculus. Don't worry about it. Just follow along. See if you get as much out of it as you possibly can. Put it in your binder. Keep it as a reference source for some time in the future when you might need it. Okay? Put this together with your R script for the first example. Put this together with your R script for the data set that is for the assignment for this week. Okay? Keep it in a folder so that you have a resource at the end of the semester that shows you how to do all this stuff. Okay? Then, when we come back next time, we're going to do a little bit more on confidence intervals. We're going to do a little bit more on t-test, and I'm going to show you some different ways of approaching t-test. There are different kinds of t-tests. I'm going to give you some examples where the t-test fails and explain to you why it failed and how to do it better so that it doesn't fail. And then we're going to move from that to analysis of variance. And I'll explain why we're doing analysis of variance instead of just multiple t-tests. Okay? Then we'll spend a little bit of time talking about different kinds of analyses of variance, different designs, before we move into regression and things of that sort. Okay? So if you don't already have login credentials for the web page, email me tonight. I will respond tonight, okay, and get you the appropriate login stuff. I'll email you an invitation again if I have to. Make sure you look at the videos that are up there. Look at those videos on the normal distribution z-scores. There's a series up there, really good. They explain it in a very simple, non-mathematical way. It's very nice, okay? Download these notes and start the next homework assignment with R. And if you have problems with it, email me and let's get it figured out, okay? I'm going to minimize the amount of math stuff in here. There's one thing on here that we didn't talk about that I do want to talk about next time, and those are the rules of expectation and variance. And the only reason I want to talk about the rules of expectation and variance is because I'm going to need those when we talk about analysis of variance. Okay? So read over that. They're on the very back, on the very front page, those things right there. Maybe you've seen some of those operators in a science paper that you've read, E, and you're going, what the hell does the E mean, right? That's the expectation operator. VAR is the variance operator. We will need that stuff when we talk about ANOVA models. We only need to, you don't have to do anything with them. You just need to know what we're talking about and what it's doing. No hard math or anything of that. It's just remembering it up here, okay? All right, see you guys next week. Be sure you, if you can't log into the webpage, be sure you email me tonight so I can get you set up. Yeah, so these are the little videos that you want to watch right there. Okay, oh no, well there's the article for the confidence interval in the t-test. So that's my little video, that's my instruction video. Those are the three little easy peasy videos that explain probability distributions.
I have some data
For the flying squirrel weights, that's the same data set that gets used in that thing right there. You're using the same data set.
Is this the instructions for the assignment?
Can I see you?
Installing our studio, that's doing box plots, and right there, in that video, you're going to get the instructions on how to add to that one.
Okay.
Okay?
So everything is explained in the videos
Yes.
for the assignments? Okay, I'm not used to this format.
Yeah. Well, I'm trying to set it up because I'm guessing that within a couple of weeks or so, we're going to go shut down.
Yes, I am too.
I just want to get to the point where it's functional, that we can get through this semester.
Yes. Why do you insist on not using Moodle?
There are a couple of reasons. Number one is the